Good morning from Vibrant Technologies. This is Mark Richardson, and I welcome you to our October/November webinar. For those of you that were with us last week, we ran into a few gremlins right before the webinar, so we had to cancel that one, and we thank you for joining us this week. If you are back, if you're new, welcome as well. This is not to replace our November webinar. We haven't scheduled that yet, but we will have one in November. And depending on how the holidays shake out, we may have to move our dates a little bit. Usually it's the third week of the month, but the third Thursday of the month. We may have to adjust that a little bit for Thanksgiving. So we'll get an announcement out soon for that. Anyway, I am joined by my dad, Mark Richardson Sr., and today we are going to be doing correlating spectral measurements. And this is also going to be part of our IMAC presentation if you attend the IMAC conference, which I believe is in Orlando this year in February. And just a couple of housekeeping notes as we're going through the webinar here. If you have some questions, feel free to type your questions in the question dialog box on the right-hand side. Additionally, after the webinar, if you have some questions, you can always email us at webinar@vibetech.com, and we can get those questions answered for you via email. Additionally, we are recording this webinar, so we'll have a copy of this webinar up on our YouTube page, usually in a couple days' time after the webinar. So I would say sometime middle part of next week we'll have this up on our YouTube page, so you can go back and view a recording of this. With that, I'll hand it over to Mark Sr., and we can get going here.
Okay, thanks, Mark. Welcome to you all, and this will be a recording, so as Mark mentioned, we can it'll be on the YouTube, and you can actually go to the YouTube from MEscope. So if you're an MEscope user, in the opening screen there's a link that you can click on. It'll take you right to our YouTube videos, and we have quite a collection of them out there now, going back quite a few years, but we are adding these monthly webinar recordings also. So they're a little bit rough. They're not marketing material, they're more of training material, and today we've just got a lot of material to cover, so I want to get into it right away. I put together a few PDFs of our presentation, which will occur in February next year. The other thing you can do, the two papers that we're going to be presenting at this International Modal Analysis Conference are already out in the cloud. So if you type in papers.vibetech.com, it'll give you a list of the tech papers, and this particular paper I think is paper number 70, all the way at the bottom of the list, and you can go read more of the details. I'm going to go through a few slides here just to introduce our topic for today. We're going to use a metric that we've added into MEscope. It's been in here for quite a while, and we're just finding more uses for it now. It's called SDI. And that stands for Shape Difference Indicator. Now, many of you may be familiar with the Modal Assurance Criterion, or MAC. We also have that in MEscope, and we use that for comparing two mode shapes, or two ODSs, or two sets of complex data that we can define as a shape. SDI is very similar. It has slightly different properties which we like, and you'll see the applications here today where we use it. And MAC would work also, but SDI has, well, we'll just look at the details here. What we have defined, and these are two new terms that we're using now, ODS correlation in this tech paper, and we'll see how we use that in MEscope. SDI indicates the difference between one or more current versus baseline spectral measurements at each frequency. So if you think about an ODS and how we use MEscope to animate the cursor position in a set of spectral measurements or time measurements. If their magnitude and phase are relative to one another, they have correct magnitude and phase, then we display that data on a model of the structure, and we call that an ODS, or an operating deflection shape, or simply a deflection shape. So we deform the model using the data from the cursor position. We're going to use, we call this ODS correlation because we're going to compare two sets of measurements, current versus baseline, at each frequency, and draw that up on the screen. So you'll see that in a minute. The second application of SDI is what we call measurement pairs correlation. Now, MAC has been used for this also, specifically for comparing FRF data. In curve fitting, in MEscope, when we curve fit FRFs, we draw up the fit function, and we also put up something called FRAC, Frequency Response Assurance Criterion. That is a comparison of the fit function versus the data over a band of frequencies. So we're going to use SDI in the same manner. We've given it a new name, and we'll look at comparing current versus baseline spectral measurements over one or more frequency bands. Okay, let me go into a little more detail here on the difference between MAC. Here is a plot. We've shown this one before. We've used it in other presentations of MAC values between a pair of shapes. Now, these are very simple shapes. One of the shapes has values of 1 and 1 in it, shape A. Shape B has values of X and Y, and then we vary the values of X and Y over a range of values, and so MAC is plotted up as a function of X and Y for the B vector versus the A vector. And there's a little formula there for MAC. But what you can see in the picture here is that there's a whole straight line of values along which MAC is equal to 1. So up here in the text it says that MAC is a measure of the collinearity of two shapes. They can be complex valued, they can have numbers in them, anything we like. If I compare two shapes and they lay on the same straight line, then their MAC value is going to be 1. If they don't lie on the same straight line, then it's going to be something less than 1. So MAC values always go between 0 and 1. In the red area here, if one of the vectors is one of the shapes, let's say the B shape is at right angles to the 1, 1 vector, then the values will go to 0. Okay, let's look at SDI. What does it look like? Slightly different formula, the same two vectors, A and B. A has got components of 1 and 1, and B has got X and Y, variable components. So we plot this function up, and you can see that there now for SDI, there's only 2 places where SDI will be equal to 1. Everywhere else it's going to be less than 1. So it's got the same properties as MAC. Its values go between 0 and 1. So it's, some people like to call it a correlation coefficient. Statisticians use a terminology like that, or a correlation factor, or we just call it a shape difference indicator to give it more of a, you know, this is what it's doing, it's measuring the difference or indicating the difference between two shapes. So if the value is 1, then the shapes are identical, or you can see plus or minus. Now we actually in MEscope, we square the SDI value, so even if one shape is negative of the other, the answer is going to come out to be 1 when they are equal, when they have equal components. When they have different components, the value is going to be less than 1. Now in MEscope, in our monitoring software, we're going to get to this probably at the end of the discussion today, we have something called Fax, and that stands for Fault Correlation Tools, and it's built into our console monitoring software. And Fax actually computes the SDI between two shapes and gives you what we call a fax bar. So the fax bar, if it's equal to 1, it's a green bar. If it's as it goes to 0, it turns into a red bar. So we'll see that, and we use that in our machine monitoring software. So we're going to look at that as a second application. In the first application, I'm going to actually impact the Jim beam here with an impact hammer. Now here we're showing you what we're going to get here when we do that. I've got a triaxial accelerometer mounted on the Jim beam. Let me scroll down here. Here's a picture of it, and then we'll turn the camera on here in a minute. So the Jim beam has got an accelerometer just stuck on the surface. Doesn't matter, because this is going to be our baseline measurement, and we're going to compare when we impact with the hammer. We're going to compare the current, we'll call it a reference measurement, to the baseline measurement. And if those two measurements are exactly the same, in other words, if they correlate well, then we get a value of SDI over the whole frequency range between the baseline and the current measurement of equal to 1 or almost 1. So this is almost like a coherence function. Now over here on the left in the picture is in fact the coherence. So the coherence, remember, if you're used to making measurements with an analyzer, or in the case of MEscope, we can do it in our acquisition window. The coherence is a different correlation between the impact force and the response acceleration. And so if it's an indication whether we're making a good measurement. In other words, is the response I'm measuring linearly related to the force that I'm measuring with the hammer. So we use the coherence to compare our measurements, or compare the two signals for a measurement, and if the values are all 1, then we've made a good measurement. And you can see in this case that the values of coherence will drop when the response of the Jim beam is very low. This is the same over here with the ODS correlation. Again, the ODS correlation is comparing a baseline set of measurements with the current measurements. So I'm going to go ahead, and here's a case where I impacted a different point. You can see here we're going to impact at different points on the tip of the Jim beam here, and if I go back and hit at the same point, then my straight line will show up here, the ODS correlation. If I hit at a different point, I get an ODS correlation. It looks like this, where I get a lot of dropouts because I haven't done a repeatable impact. Well, when would I want to do a repeatable measurement like this? If I'm doing what we call a roving response sensor impact test. Now, the more common impact test is a roving impact test, where I rove the hammer around and hit the structure at different points. But the advantage of a roving response test, and that's in fact how we tested the Jim beam when we got 3D motion of the Jim beam for the various resonances, we roved a triaxial accelerometer, just like this one here. And if you're going to do that, then you have to ensure that you're always impacting at the same point, because you want to excite the structure at the same point in the same direction each time you make a measurement. This is a typical setup: triaxial response, 4-channel analyzer here, and so that is what we're going to do here. So let's go ahead and do this measurement. Let me give you a little view of our live setup here. Here's the Jim beam, and here I put my hand out here so you can see that we're live. And The accelerometer is just as a reference so that when we compare a baseline with an impact, we can see whether we've done a repeatable impact or not. So let me go ahead and fire up MEscope, and we'll see how all this works. Let me put some of this stuff off of the screen here. Well, maybe we can just leave it there, and let's bring up MEscope. And I'll make it large. So here's MEscope set up, and it looks very similar to the graphics that I showed you before. So over here on the left is a data block with 3 FRFs in it with the coherence overlaid. So that's a display format where we overlay by DOF, where the coherence has the same DOF as the FRF, so we can overlay the two measurements together, or the two calculations together, the coherence and the FRF. Over here on the left is my baseline, and then down below it is the ODS correlation. And you can see it's the last time I ran MEscope, I did a pretty good job here of hitting it at the same point and direction so that my ODS correlation values are all equal to 1. Those are the SDI values. Well, let me go ahead and start this. Now I have some hotkeys up here. The first one is for impacting. The second is to reset the baseline. And then I have a couple more here. I can actually go and animate the mode shapes if we want to look at these mode shapes of this this particular, the mode shapes we've taken off of here. So we can see when SDI values are high, that means that for a particular measurement, maybe the mode shape components for the two different points where I impacted are essentially the same. So again, the ODS correlation is going to give me a strong correlation between the current and the baseline as a function of frequency. Let me go back and hit the acquisition here, and it's going to come up and it says, are you ready to impact? So I'll say yes, and I'm going to go over and pick up the hammer, and it's waiting for me. I've got the ACK window set up to trigger, and I'm going to take 2 averages. Again, I can't look at coherence unless I take at least 2 averages. The coherence of a single average is always 1. This is a measure of collinearity, so we've got to take some extra data here. Oh, I hit it too hard, so let me hit it a little more gently. There, I got a good measurement, and I'm going to hit it again. And there it is. So if we look over here, that was a pretty good measurement with 2 averages. And again, you want to hit in the same spot, otherwise you're averaging apples and oranges together. You don't want to be doing that. Now it says do you want to check repeatability? In other words, the ODS correlation. So let's go ahead and do that. And you can see my ODS correlation looks pretty good. So compared to my baseline, I hit in the right spot. And I actually hit it twice in the right spot because the coherence is telling me that I got some good data over here. All right, well, let's dismiss this. Let's update the baseline with this measurement. Since I made a pretty good measurement there, I'm going to say update the baseline. Now you can see that when I compare the current with the baseline, all my ODS correlation values are 1 because I'm comparing these 3 complex spectra with these 3 over here. And as a function of frequency, they're identical because I just took the current and replaced the baseline with the current. So now I'm going to go back here and I'll just I'll hit at a different point here and we'll see what happens. So are you ready to impact? Yes. I'm going to just hit over here on the back side of the of the gem beam. And you can see I'm getting a bunch of stuff on the screen here, but so there it is. You can see the coherence was not too good because I didn't hit in the same place twice. So let's do that one over again. I'm going to turn off my, let's just get rid of that so it doesn't keep popping up on the screen here. Oh no, yeah. All right, now we're going to start over here. And you can see the impact as I hit the structure. You'll see the impact in the middle window here. There's the impact force from the last one. So let me just see if I can hit it in the same place twice. It's the old joke about not hitting in the same place twice. Well, look at what happened in my ODS correlation. It dropped way down because I hit in a completely different place than where I hit for the baseline. Well, let's go back and see how well I can actually hit at the baseline or at the impact point for the baseline. That was out here somewhere on the end of the beam. You can see we're getting a little picture flash up there. That's kind of good. Okay, let's check repeatability. Not too good. So I didn't hit in the right spot. Let's try it one more time here. Out here on the end somewhere. Oh, are you ready to impact? Yes. Overload, too hard. Kind of a double hit there. Still an overload. Not too bad. The coherence looks very good. Let's check the repeatability. Better, but not perfect. Let's update the baseline with this data. And I'll see if I can hit in the same place. Pretty good measurement. Well, it was better. I got closer. You can see that we got a drop out here where two of the three FRFs have very little response in them. So that's not correlating very well with my baseline. And you can see that even over here at that frequency, the coherence is dropping also, especially in the Z direction here. So this is X, Y, and Z of the accelerometer. And so it all makes sense that when the ODS correlation drops below 1 and the coherence also drops below 1, then we just don't have a very strong signal at that frequency. Okay, well that is pretty much what I wanted to show you for the repeatability. The other advantage of using this would be in a route-based monitoring program. If I am using magnetic sensors, accelerometers, and I place them on the machine, well, you want to ensure that when you make measurements from various points on the machine, that set of cross-spectrum data or auto-spectrum data can be used. In other words, it correlates well with a baseline set of measurements that you've taken on that same machine. So in a route-based program, you'd be taking data, let's say on a weekly basis or a monthly basis. You want to make sure that if you're alarming on peaks and various things like that in the spectrum, that at least you've got a set of data that's repeatable. In other words, you put the magnet in the magnetic accelerometer in the right place and took the same data that you took last time. So that would be a monitoring application of this repeatability. And MEscope, this is all being run in MEscope with scripting. And a script, if you're not familiar with it, is simply a spreadsheet with MEscope commands in it. So when I press a hotkey, the hotkey executes a script, and the script executes a sequence of MEscope commands. So that's what we're doing here to automate the process, and then of course we can come back in a monitoring program and do this, import data from a, let's say, a portable collector, and do this type of verification that our data is repeatable. Okay, I'm going to stop this, and we're going to move on to the second application of SDI. Let me just close this project. Okay. I'm going to open up this called measurement pairs correlation. So we're going to look at the second way to correlate measurements, and here we're going to correlate 4 autospectra. Let me go back to the camera here, and so we're going to turn on this machine in the back. I've got a different 4-channel analyzer, so let me disconnect from the first one and plug into the second one here. Remember, Vibrant is a software company, so we're agnostic when it comes to hardware. So I've just attached a National Instruments 4-channel. This previous one was a data translation, but they're very similar. All we're doing is pulling the time records out of these analyzers into MEscope and doing all the post-processing there. So let me just put this back down, and I'm going to start the machine. So let me just turn it on, and I've got 2 triaxial accelerometers mounted on the bearing blocks of the machine. Let me put this up, and you can see that. Now this is a different model. This is one of our other rotor kits here, and let me just move this back so we can see what's going on here. Okay, the analyzer is starting to initialize, and it's pulling in data from the rotating machine off of those accelerometers. Now, the accelerometers have 3 channels each, but I've only got 4 channels, so I'm only measuring the horizontal and vertical motion of the machine on the bearing block. So you can see over here on the model, this is another feature in MEscope with the acquisition window. Once I've got acquisition set up, it will, and then I link it to a model, it will show me on the model where in fact the data is being acquired from. So this is a very handy thing for doing a pretest, setting up your test, especially if you're impacting. But in this case, if you were doing route-based collection, then it shows you, where they need to be mounted, the accelerometers, and the data that's going to be acquired. All right, we're bringing data in. On the top here, this is the acquisition window. In the top of the window, let me just make this large and we can take a look, is the 4 accelerometer signals. And let me just show you how we set this up. Once I set it up in the acquisition window and save it, then all these parameters, when I open it, are going to be be still there. So this is an auto spectrum that we're computing down here on the in the bottom for measurements. They're being computed from the vibration signals that are coming in from the acquisition front end. In this case, it's a 4-channel, what we call an analyzer. Here's my frequency setup, my sampling. I'm taking 2,000 samples of time domain data, which has given me 1,000 samples of spectrum data. Here's the frequency range. I'm only going to get one sample, so I'm not doing any averaging. And you can see the peaks in the data down here. Now, something else you can do in the ACK window is if I set my units up, and you can see my units are in inches per second. So MEscope is automatically integrating this data to display it in inches per second, even though it's accelerometer data coming in from the accelerometers, or it's acceleration data. Let me see if I can pull this out here. If I click down here, you can see the units of these auto spectra. They're still squared. We haven't taken the square root here, so they're inches per second squared. That's what we would call an auto power spectrum of each of the signals on the top. So let me go back here and put this back and show you what else is going on here. Let me just hit this key again, and it should put everybody back in the right place. Well, here I'm going to stop and start over. You see I have these are hotkeys. I have a start key, a stop key. This one is for updating the baseline data. In this case, it's going to be auto spectrum data. And this one here is for archiving the data into an archival database. Let me go back and start this back up again. Because in my script, I got some other things going on here. And not sure that it's behaving the way I want it to. You see the band cursor is jumping along here, and it's actually comparing in 3 different frequency bands this data. As it acquires it, it's going to compare it with the baseline. And then I can update the baseline at any time. I'm not real happy with what I'm seeing here, so let me see if I can get this to behave a little better, because I want to get the first order peak here. See, it's grabbing the second order peak and saying, okay, so let's see here. There we go. So now I'm really exciting the first order. So as you can see here, there's a nice big peak. These first 2 measurements are coming off of the bearing block, the outboard bearing block, number 1 over here. And then these 2 down below are the inboard bearing block. And you can see I've got a huge peak here at the 4th order, it looks like. Well, we're only going to compare baseline and current for the first 3 orders. Anyway, I've got a nice strong order peak here, baseline peak. What is the speed of that? Well, I'm using variables in these measurements. Let me see if I can get that up so we can actually see what that frequency is here. I'm going to go here and well, let's move on. We don't really need to know the frequency. I'm going to go over here and let's stop this. Stop it. And now we're going to start the actual monitoring of the machine. So we still got the acquisition window. It's moved over here to the left. In the middle are my current measurements coming off the machine. And over here is a shape table with SDI values in it. So what we're comparing here when we do shape pairs correlation is we're putting SDI values into a shape table for each of the 4 measurements and each of the 3 frequency bands. So I've got 12 numbers in here that are telling me the correlation between my baseline and my current measurements. Now, if I update the baseline, I'm going to push this button right here to update the baseline. All these SDI values turn into 1. Let me do that again. I'm going to update the baseline. You see, they all become 1 because now my current and my baseline are identical over those 3 frequency bands. The bands are 1,000 RPM wide, so we can have the machine move around a little bit, and in terms of the speed and the running speed in these orders. And what we're doing is grabbing the peak of the running speed and then multiplying by 2 and by 3 to set up those other 3 bands. Okay, so this is all working. I'm going to push the button here that says archive data. Now it's going to start putting data into our archival database. And let me pull this over here. We'll just set it there on the side. And now I'm going to start a separate program. Right now we have this as 2 different programs. Eventually it's all going to be part of MEscope with our newer software. And so then I can have, what we've got here is MEscope pushing data into the database under script control, and console is mainly a graphics post processor. So what we've got here on console are 3 different graphics windows. I've got gauges here. Those are my 4 accelerometer auto spectrum values, but what we're logging into the database are the SDI values. So if I click here, let's make this large. So I'm going to make this this is a trend plot of 3 of the SDI values. 1 value for each of the 3 bands. Remember, we've got 12 numbers coming in, 12 SDI values, the 3 bands, and then the 4 pairs of auto spectrum data. So that's what we're looking at here. And you can see all these values are very close to 1. In other words, when we updated the baseline over here in MEscope, the values are all going to go back to 1. And the machine is vibrating and it's varying, moving around a little bit. Let's put the pictures back. Here is the fax bars down here. Now these bars are saying how close do these numbers that are coming in from the machine match a baseline set of data that I've saved in the database. Now if I go up here and update the baseline, the fax bars jump back to 1. So here we're using fax, and then they drop back down again right away because we got some variation here in these, and these are the 3 different frequency bands of the machine. You can see my gauges are turning red because, again, compared to the baseline, the machine is changing. So this is quite a varying machine here, although these values are they're all fairly high. Let me go here. I can actually control MEscope remotely through the database from this program we call the console. So if I update the baseline, all these trend plot values should jump back to 1. Let's see if that in fact happens. Yeah, see here they're going back. Now I'm going to update the baseline that's stored into this in the archival database, and now you can see that my values are up to 1, but the machine is bouncing around, vibrating quite a bit, and so this is showing me, you know, how well the 4 auto spectra are correlating with between the current and the baseline. And the fax is giving me a live indicator of, is this data the same as our baseline SDI values, the shape with basically 12 numbers in it. That's what's being archived over here. If I go back here and just look at, here are the SDI values going into the database. And if I update the baseline here, you'll see they all turn back into 1. And those values are now being archived into the database, and the fax bars over here are comparing those with its baseline. But you can see quite a variation here. This is a very strong indication of how well these measurements on this running machine are matching up as I take new data and compare it with the baseline. All right, well, that pretty much wraps it up, Mark. I guess we're going to finish a little bit early. Let me turn this machine off. Well, the other thing I was going to do is vary the speed, and we'll see. Let's just change the speed here a little bit of the machine, and that should cause the vibration levels to change quite a bit too. So I just cranked that up, and let's just see what happens to our trend plot here. Those values should drop significantly compared to the baseline. We'll just let that run for a minute. You can see the fax is saying this is quite a bit different data now that's coming in. Let me make this large so you can see. So the first and second orders are significantly different. The third order, it's saying there isn't a whole lot of difference there, but you can see over here the third order is actually, let me make this large so we can see what the third order looks like. But at this higher speed, the machine is just a little more consistent. We get some nice strong peaks there in the first 3 orders. So again, this is X and Z directions, horizontal and vertical on the outward bearing, and these two down below here are X and Z, horizontal and vertical, of the inboard bearing. Quite a difference between those two bearing blocks and how this machine is vibrating. Let's drag this back over and see how our trend plot is doing. Well, you can see the values are just jumping all over the place here. And we got some lower values in the trend plot. And Fax is saying, well, the third order doesn't seem to be changing a whole lot. Well, it was quite low before, and but if I change the speed, I should get, I'm going to crank it even a little bit more here. Let's update. I'm going to update baselines, both the spectrum baseline. Uh-oh, I can't update there. Let's update it over here then. So we'll update it here. And we'll go back and update the SDI. So here we're back to correlating very well at the higher speed. And let me just drop the speed back down and see what happens to our correlation. Well, Fax immediately indicated that we have a difference in the spectrum. With that, I'm going to turn off the machine and we'll stop the acquisition. Do we have any questions, Mark?
No questions at this time.
All right. All right. Well, then let's just wrap it up, and we will announce next month's webinar. We don't have the topic settled yet, but we'd like to show you some new things. Maybe we'll go back and review some old things. So hopefully we'll see you next month, and have a good rest of your week.